A neutron walked into a bar and asked, "How much for a drink?" The bartender replied, "For you, no charge." Why is a physics book always unhappy? It has a lot of problems. Why can't you trust an atom? They make up everything. Where does bad light end up? In prism. Absolute zero is cool. Hello friends, welcome to physics class. Welcome to another week of online learning. I hope that you're enjoying how I've laid out the assignment packets. And so yeah, let's dive right into this week's content. Over the past few weeks, we've started to build our foundations so that we can tackle electricity in the macroscopic sense. We started with charge, where we're looking at a charge of a particle or maybe two particles. And then last week we used Coulomb's law to find the force associated between two charges. This week we are looking more at electric fields. So what we're doing each week is we're building, again, our foundations. So we're starting small, literally, and we're building it up so that we can tackle it at the macroscopic sense. Once we have those tools in our arsenal, so we're able to think about these properties and scale them up, we can go from charge to force to electric field, and then scale that up to a lot of charges. So, for example, a bulk material like a piece of metal. And we can look at its electric potential, which we'll get to next week. So from here, we're actually going to get into how can we use these properties of charge to do electric work. Again, all this comes back to conservation of energy and how we can use that energy to do useful work. Ultimately, I want us to get to circuits and magnets, and I think we're on a good track. And there are a couple of really good online labs where you can design your own circuits and kind of toy with magnets. And while I would like for you to do that in a hands-on lab, I think that given the circumstances, this is a pretty darn good alternative. So, what is the agenda for this week? This week, we will be going over more on electric fields. And again, we're starting to scale this up. So instead of looking at one or two charges, we're starting to look at a bulk material property. We will also briefly go over some insulator and conductor theory. And finally, in each Zoom class, I will go over this in more detail, but we will be talking about our end of the semester, end of the quarter movie project. Quick side note, if any of y'all have a science question and you want me to go through it, you want me to explore it a bit more, and maybe make like a little video about it, feel free to email me, feel free to message me about it. Again, my background is across multiple fields. I know a lot about chemistry, I know a lot about physics, and I know a lot about biology. So if you have questions, feel free. I'd be happy to answer them. Don't forget to give your dogs a big ol' hug on Friday, because it's National Hug Your Dog Day. This week, we will be focusing on electric fields, and you were introduced to this topic a little bit last week, but this week we're going to dive more into the theory of it. Okay, before we actually get into the physics theory of electric fields, I want to give you a bit of historical background. So, this guy here, his name is Michael Faraday. He lived from 1791 to 1867. And Michael Faraday is the one who named, he actually really discovered the electric field. He called them lines of force. Michael Faraday actually grew up as a bookbinder apprentice. I don't think they really have those jobs anymore. But he read some science books and was really interested and ended up then apprenticing for basically a scientist. And this is how he got into his discoveries, which is pretty neat. Not everyone has a clear-cut path through their life, right? I do want to note, though, that Michael Faraday is super duper duper important for a lot of different physics ideas. He was really, really important for a lot of electricity and magnetism and generators. And he actually heavily influenced a guy named Heinrich Hertz, which, Hertz might sound familiar to you, like a radio station frequency. So Michael Faraday was super duper important. Let's provide a little context for why we care about electric fields. In the past few weeks, we've looked at charge. In particular, we have looked at like charges and how they repel, or opposite charges and how they attract. We then took these ideas and asked, how much electric force do they feel? And we defined that electric force using Coulomb's law. So the force is equal to the constant times the charges over the square of the distance. Let's start taking these concepts between a charge or two charges or just a few charges, and let's scale it up to a bigger picture idea. And this is where electric fields come into play. Let's start by defining what an electric field actually is. So, an electric field is a force field of sorts around an electrically charged object. And I have force field in quotes here because it's not like a physical manifestation. It's not like if you put a charge underneath a microscope, you would physically see this force field. But we have a convention for how we draw these so that we as people can conceptualize this idea and apply it to electricity concept. So how do we visualize this force field? We visualize this field with arrow lines around a charge. I will show you what I mean by that. Let's say we have a positive charge, Q. Remember, in Coulomb's law, we used Q to represent the charge. Let's say we have a positive charge here. The electric field around it, we visualize with arrow lines. So arrow, arrow, arrow. This is how we visualize it, and this is what you started to see in that online lab. Let's take a negative charge. Arrow, 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 arrow. Okay. Notice how my positive charge has the arrows pointing away and my negative charge has the arrows pointing towards it. This is specifically the convention we use, okay? So this is convention. Do not flop. It's supposed to say flop. Positive charges always have the electric field lines coming out, radiating out from it, and negative charges always have the electric field lines coming in towards it. This is the convention. You cannot flip-flop them. So put this in your brain. So just to make sure this stays in our brains, so arrows point towards a negative charge. Arrows point away from a positive charge. This is all fine and dandy, but you might be asking yourself, okay, why do we care about an electric field? What does it physically represent? What I can say is that the magnitude of the electric field is equal to the force on a charge over the amount of charge. Stated another way, the electric field, E, is the amount of force per charge. How much force does each charge feel in our environment? So that's qualitatively what it means. Let's think quantitatively. So our electric field, E, is equal to the force per unit charge. This is one of the main equations you will be working with. The units for this, the unit of the electric field is newtons per coulomb. And that makes sense because we know force is in newtons and we have charge in coulombs. An important note that we will return to in a little bit is that you already know how to solve for this force. This is based on Coulomb's law, which you worked with last week. So we're connecting ideas, yay! Let's look at a practice problem involving the electric field. We're told that a positive 2.8 microcoulomb charge experiences a force of 0.25 newtons. What is the magnitude of the electric field? First, I'm going to write down everything that I know. So I know that my charge is positive 2.80 times 10 to the minus 6 coulombs. I know that the force is 0.25 newtons. I also know that my electric field equation is E, the electric field, is equal to the force per unit charge. This is just a plug and chug problem. So I have 0.25 newtons divided by positive 2.8 microcoulombs. And when I plug that into my calculator, I get, just write this out, 0.25 newtons over 2.8 times 10 to the minus 6 coulombs. And when I plug that into my calculator, I get 8.9 times 10 to the 4th newtons per coulomb. One of the cool things about a lot of these fundamental electricity equations is that they're really interconnected, and you can flippy-floppy and swap around a lot of their forms. So for example, I just defined for you the electric field equation. But let's say we're interested in finding the amount of force on a charge. And this is going to become, I feel, a little bit more clear later on when we start to explore things like capacitors and really like fundamental stuff for electronics, okay? So bear with me. Let's say we want to find the force on a charge due to the electric field. Well, I can just swap around this equation, and I can find that the force on a charge is equal to Q times E. We'll see more of a context for this later on, okay? So we can flip-flop this equation around and then solve for a value. Let's look at a second practice problem. In this problem, we are told that we have a uniform electric field and that it has a magnitude of 4.6 times 10 to the fourth Newton per Coulomb. We want to find the magnitude of the force exerted on a negative 9.3 times 10 to the minus 6 charge. Key words here: find the magnitude of the force. So I don't really care if this charge is positive or negative. I just want to find the magnitude of it, okay? I gave you in the last set that the equation for the force is equal to Q, the charge, times the field. So that's what I'm going to do. I'm going to plug and chug. We know that the electric field is 4.6 times 10 to the fourth, and we know that the charge is negative 9.3. I'm going to plug those values in. So I have the force is equal to, I'm going to say the absolute value of the charge. So that's absolute value of charge times field. So that's 9.3 times 10 to the minus 6 coulombs times 4.6 times 10 to the fourth Newton per coulombs. You see that the coulombs cancel. And we are left with a force of approximately, let me plug this in, of approximately 0.428 newtons. I told you that Coulomb's law would come back to this equation. And we know from last week that we can find the value of the electric force between charges. And we know that is just equal to Coulomb's law, Q1, Q2 over R squared. So I can swap in this equation. And I'm going to simplify it a bit. So we have E is equal to K, Q times Q over Q times R squared. So in this case, we're looking at essentially just a test charge. So I can say this is just Q, Q, and Q. And from that, we can see that we can cancel out a set of charges in which we are left with K times Q over R squared. So all we've done is swapped in Coulomb's law to find the force associated with an electric field. And you have a problem in your assignment set dealing directly with this. I'm not going to work through an example because it's really just a plug and chug. But just know that we can connect ideas from last week to this week. So far, we have looked at how to quantify an electric field surrounding a charge. Let's start to scale this up. So at first, we looked at one charge. Then we looked at two charges. Now, let's start to scale this up so that it's a little bit more macroscopic. To understand these concepts more macroscopically, we have to have a good foundation in how the smaller pieces interact, right? And something I want to point out is that electric fields have distinct shapes and patterns. This concept, although it might seem a little bit obvious, okay, yeah, charges interact in certain ways, right? This concept is important because, again, when we scale it up to the macroscopic level, a lot of these fundamental interactions and characteristics carry on as you scale these ideas up. So I'm going to show you a diagram from one of the textbooks. Bear with me as I place this. Okay, there we go. Let me focus that. There we go. Oh, that's good. Okay. In these examples, we are looking at two charges and how their electric fields interact with each other. For example, let's say we have two positive charges. We know that like charges repel. So you could imagine that those little invisible force fields, electric force fields around them, would bow out and not contact each other. This is a characteristic shape of two like charges coming together and what their electric fields look like. Let's look at two opposite charges. So we have a positive and a negative charge here. Ignore these tangents for right now. Just look at the overall arrow line shapes. We know that opposite charges attract. And so you can see that these electric field lines, again, radiate outward from a positive charge and move towards a negative charge. And finally, we know that the magnitude of the charge matters. Think back to Coulomb's law. The bigger the Q, the bigger the force, right? So this is an example where we have opposite charges, but one charge, the positive charge, is double in magnitude. So look at the density of these field lines. So again, these interactions have characteristic shapes, and that is super duper important for when we think about electronics. I keep telling you that these concepts are important macroscopically, but I haven't really given you an example yet. So let's do that. Let's talk about a parallel plate capacitor. These are actual items that are used in circuitry. And I'm going to try to draw you a picture, okay? When we say parallel plate, you could imagine, there might be two parallel aspects to this. What this looks like is this. We have two parallel plates, and a capacitor is able to store electrical energy. You see these on circuit boards. They are used in their designs. If you're interested, I can try to have my husband do like a little workshop on it. Maybe he is a software developer, and he can actually design circuits in his head. So if you're interested, shoot me an email or message me on Discord. These parallel plate capacitors really, really fundamentally rely on the ideas of the electric field. One side of the plate is positively charged. The opposite side of the opposite plate is, you guessed it, negatively charged. Think back to those diagrams you just saw in which we have electric field lines going from a positive to a negative charge. Let's see what this looks like. We have a uniform electric field. That uniform electric field is fundamental to this type of capacitor and how we use it in electronics and circuitry. So again, we can see we build up the little ideas to the macroscopic. I keep talking about how we are learning the foundations so that we can apply them to the bigger ideas and bigger topics. And I want to actually show you an example of what that means. So we just discussed how this capacitor stores electrical energy and it utilizes this uniform electric field. I want to show you what a capacitor in real life actually looks like. So they come in different sizes and slightly different shapes, depending upon how much charge they're going to store. This is a capacitor. This is a very big one. We can see we have leads here, the terminals. We can also see it has the specs listed on the actual thing. And we'll get to the specs at a later time. That's more circuits, okay? I got this next example. My husband is a software developer and computer engineer, and he designs circuits for the projects he does. Just fun projects. So this actually what he designed to control LEDs for a project he was doing, and it has a couple different components. You can see some resistors soldered down there. But what I want to point out is, see this tower kind of deal, this cylindrical tower, this is actually a capacitor. So this size versus that size. Also, that little brown speck there is also a capacitor. Yeah, just this stuff is really neat. And these, these devices all rely on these fundamental ideas that y'all are learning right now. This is our last segment for this week's assignment module. And now that we've talked about charge and we understand its properties a little bit better, I want to introduce, well, I know you've heard of these words before. So let's talk about insulators and conductors. Let's define what is an insulator and what is a conductor. So let's start with insulators. I know that you're familiar with these terms in your day-to-day lives, but let's give a little bit more definition to it. So an insulator impedes the flow of electrons. You're familiar with insulators. Generally, you think of non-metals, generally. And you also think of insulators as having low conductivity, right? A current doesn't normally run through an insulator, so this has low conductivity. Conversely, let's look at a conductor. So it's the inverse of what an insulator is. So a conductor allows the flow of electrons. This means that it has high conductivity. And when you think of a conductor, you generally think of metals. Let's look at some examples of conductors and insulators. So again, for conductors, you generally think of metals, so like silver or gold. You know, think of wires, right? So we think of metal wires, and we have insulation wrapped around it so that, you know, we don't get zapped when we touch it. So we also can think of steel. Ooh, seawater is a really good one. So I want you to think about, why would seawater be a conductor versus totally pure water? I want you to think about that. We think of insulators like rubber and glass and, you know, oil, diamond, dry wood. So again, that electron flow is really impeded in insulators. Why does this matter in the bigger picture? So let's look at insulators and conductors. So again, conductor, charge flows freely. So if we take two objects, or two points, two objects, right? And we connect them via a conductor, we can see that these electrons flow, whereas in the case where they're connected by the insulator, they don't flow. These ideas are really important when you scale this up to, you know, think about the electric wiring in your house or apartment. So again, that's it for this week's lesson. I hope you have a great rest of the week. Again, if you have any questions, reach out, email me, come to office hours, Wednesdays and Fridays from 3 to 4 p.m. Yeah, hope you have a great rest of the week. Bye, friends.